In this second screencast of Module 5, we will discuss mass transfer in the absence of migration. As we discussed in the previous screencast, migration is the force by which positive ions are pulled towards the negative electrode and negative ions are pulled towards the positive electrode. This can be a significant contributor to mass transfer. But here we first want to discuss the situation where we can neglect it. So when is that the case? To make it very simple, that is the case when we have a lot of other ions present. So here on the right side we have all these sodium ions present and a lot of chloride. So there are only a small number of iron ions here. Now in this case, then the migration term can be neglected. In this case, it cannot be neglected. Now why is that? Well, as you can see here in the equation, the migration term depends on a number of factors, including the potential gradient, the concentration, the mobility, and the charge of the ion. Now, if you have this situation, you don't have so many ions, and as a result you have a relatively high ohmic resistance and also a large potential difference between the plus and the minus electrode. This means that this term is relatively large, and also as a result the migration term is relatively large. In the situation on the right, you have many ions, resulting in a very high conductivity of this system. A high conductivity means a low ohmic drop and also hence a lower potential gradient between the plus and the minus electrode, and that means that this term is reduced, making migration much less important. But the simple rule of thumb you should remember is, with background electrolyte, migration is not important. Without background electrolyte, migration is important. Now, I would recommend you here to carry out quiz question 5.3. Now, how can we describe mass transport when migration can be neglected? Well, in a very similar way as in any other chemical reactor. So let's look at our example again here. You have the iron 3, the iron at the electrode. So how can we change this mass transfer? How can we increase it? Now, one way is by increasing the concentration of the iron in the bulk. We can also try to influence the diffusion coefficient. Of course, that's difficult because it's a certain molecule, but if you would, instead of iron, use another ion, it would also have another diffusion coefficient. The velocity of your electrolyte is important. If you have a higher velocity, you typically have better mass transport to the electrode. The cell geometry is important. The type of flow you have. Do we have a laminar flow? Do we have a turbulent flow? The temperature. Temperature always helps processes like diffusion and convection. And then there is the viscosity, where a lower viscosity is better for mass transport than a high viscosity. So these are all factors that influence mass transfer in a way very similar to normal chemical reactors. Now let's go back to the Nernst-Planck equation. We have said that we can now neglect migration, so we can forget about this term. So we are left with two terms, one for the diffusion and one for convection. Now, in principle, you can try to solve both the diffusion and the convection term analytically, but this is a lot of work and very, very difficult. So in practice, in chemical engineering, we make use of a mass transfer coefficient, KL, which describes both diffusion and convection. And then, if you write it like that, your flux is the KL multiplied by the concentration in the bulk minus the concentration at the electrode surface. Now, how does the KL, the mass transfer coefficient, relate to concepts like the limiting current density, and also to dimensionless numbers such as the Sherwood number? That is what we will explain on this slide. For this, I assume that you have a good background in these dimensionless numbers, that you already had courses on this. If not, I really recommend you to look a bit into this, because it's important to get the concept of these dimensionless numbers. So, what does it mean? What can we say? At the limiting current density, the electrode, the concentration at the electrode is 0, which means that the flux is equal to the KL multiplied by the concentration in the bulk. And this is then, if you now fill in the dependence of the KL on the Sherwood number, which is listed here. So the KL is the Sherwood number multiplied by the diffusion coefficient divided by L, you get to this. So the flux is equal to the concentration in bulk multiplied by the Sherwood number multiplied by the diffusion coefficient divided by the characteristic length. Now, you can easily then make the step towards the limiting current density, where you basically just add the N and the F. So in this way, you can relate the limiting current density to the dimensionless Sherwood number. The Sherwood number for a particular electrochemical reactor depends on other dimensionless numbers, most notably the Reynolds and the Schmidt number. And you can get then certain mass transfer correlations. So this is a mass transfer correlation. It says that the Sherwood number depends on a constant multiplied by the Reynolds number to a certain power multiplied by the Schmidt number to a certain power. Basically, the Reynolds number indicates whether a flow is laminar or turbulent, and the Schmidt number indicates the ratio between the viscosity versus the diffusivity. Now, such a mass transfer correlation can be used to describe the mass transport in an electrochemical reactor. So what does that mean? It basically means if you know the mass transfer correlation for a particular electrochemical reactor, you can use it to calculate the KL of that reactor, and so make all the necessary mass transport calculations. And here you see a number of these mass transfer correlations for typical electrochemical reactors. And especially the second one, the parallel plate system, is something we see very often in an electrochemical reactor. Because you have an anode, a plate, and you have a cathode, another plate. You don't want to make the distance between these too large because of ohmic resistance, and hence you have a parallel plate system. So this we see very often, and here you see certain mass transfer correlation. For example, this first equation is valid in a certain Reynolds regime, and this other equation is valid when the Reynolds number is higher. And you can, looking at the Reynolds values, you can see that the first one is more laminar and the second one is turbulent. You can also see that the second equation has another characteristic length than the first equation. So also this characteristic length is something you always need to take into account, and it's basically very comparable to normal chemical engineering calculations. But I must say personally that to me, when I see a system, it's not directly clear all the time what the characteristic length is. So sometimes you really need to look up, okay, for this reactor, this is the typical characteristic length. Now, how is this useful? We can use this knowledge if we want to improve mass transport in an electrochemical cell. And that's here I just show a brief example of this. This namely shows the effect of turbulence promoters in an electrochemical cell. Here you see a number of lines in a graph where the Sherwood number is plotted as a function of the Reynolds number. Basically, what we want, what we desire, is that we have as high a Sherwood number as possible, and preferably a not too high Reynolds number, because higher Reynolds number means we require more flow, more pumping power. So we want to be high here. And what we can see here is that with an empty channel, we have decent Sherwood numbers. By implementing these turbulence promoters, we improve our mass transfer properties. And apparently this particular turbulence promoter gives the best performance. As you can see here, that it gives the highest Sherwood number for a particular Reynolds number. So we can say if we are looking for an electrochemical process with a good mass transfer, then yeah, we should think of using this type of turbulence promoter. Now, to play around with limiting current density with these dimensionless numbers with mass transfer, I would recommend you to carry out quiz question 5.4 and 5.5. To close this part on mass transport in the absence of migration, I would like to briefly discuss mass transport in the presence of gas formation. Gas formation is quite common in electrochemical systems. It's either at the anode or cathode you can have a gas forming reaction. Then you get this situation where you have bubbles near an electrode and you have your reactant that wants to move towards the electrode. And you can imagine that these bubbles can help actually quite a lot, because when they form and when they detach, they cause local turbulence, and that can enhance mass transport. So this is a topic that actually has not seen a lot of research, and so the understanding of how this works is quite poor. There have been some work, and some persons have reported a correlation for that. So you can see here the Sherwood number is related to the Reynolds number and the Schmidt number, but now with these powers. And where they claim that characteristic length in this case is the size of the bubbles. Now, to be honest, there are not so many papers in this field, so I'm not 100% convinced about the validity of the equation, but for the time being, it is the only thing we have. And as you can also calculate yourself in one of the examples, is that this can have quite a profound influence on the mass transfer. So that's why I think it's important to mention it. But as said, there's still a lot we need to learn on this topic. And this is where I would like to conclude this part. Thank you for your attention.